as Eric mentioned, this title of this talk is the NOAA first MODIS SST reanalysis, or MODIS RAN1 from Terra and Aqua. I'll start by thanking my co-authors, and I want to acknowledge CoastWatch for helping us with the archival of MODIS SST dataset. So I'll start with a brief overview of the talk. So I'll start with some background and motivation for MODIS SST reanalysis, and then I'll give some background on the Advanced Clear Sky Processor for Ocean, or ACSPO, algorithm for MODIS. Then I'll do and present a validation of MODIS RAN1 against in-situ SSTs, and I'll cover how the mitigation of MODIS thermal emissive bands calibration artifacts that we encountered. So, and I'll end with covering the inclusion of MODIS SST and the super-collated SST products from low Earth orbiting satellites, or L3S LEO, and I'll end with some future priorities. So as for background and motivation, so NOAA produced SST from LEO as low Earth orbit, VIIRS, MODIS, AVHRR FRAC and GAC, and GEO, ABI, using its advanced clear sky processor for ocean, or ACSPO, enterprise system. So numerous users have requested full mission SST records, which have consistent across the individual sensors and missions. And the second request that users have expressed was the need for low data volume and higher information super-collated to L3S SST products. So in the last 2 to 3 years, we have been trying to fulfill the user's request, and we performed several full mission reanalysis or runs. So in 2021, we covered Metop first generation, and they're carrying AVHRR FRAC. So there's Metop A, B, and C, and out of those, so this dataset started in 2006, and it's still active. So this is documented in this paper here by Victor. Then in 2022, we performed the JPSS VIIRS Reanalysis 3 from MPP, NOAA 20, and NOAA 21 VIIRS. So this dataset started in 2012 with SNPP. And then we performed collation of Metop first generation JPSS SSTs into 0.02 degree gridded super-collated to L3S LEOs that we call them. So it's the AM line, that's the afternoon orbit satellites, and the PM line. So they started in 2006 and 2012, respectively. So these are both reported twice daily, 9 day, and most recently we have aggregated these 4 AM and PM day-night files into one daily file, which we call L3S LEO daily, or DY. So those are all documented in these 4 papers here. So now the topic of this talk is the first NOAA MODIS reanalysis, and this goal was to satisfy user request to extend the L3S LEO records. So this includes Terra, which has SST available back to 2000 to present, and Aqua, which extends back to 2002. So Aqua flies in an afternoon PM orbit, just like the JPSS satellite. So it's MPP, NOAA 20, NOAA 21, with a local equator crossing time of approximately 1:30 AM PM. So Terra, on the other hand, is a mid-morning AM orbit, so with a local equator crossing time of about 10:30. So that's about 1 hour later than the Metop first generations, which are 9:30 and 9:30 AM and PM. So the orbits of Aqua and Terra are maintained until in recent years. So if you look at the figure here, so this shows the delta LEXT, or the local equator crossing time anomaly. So it's a deviation of the equator crossing time from nominal. So you can see, let's just take Terra in the beginning. In the first few years, Terra was actually flying in a 10:45 AM PM orbit, but over the first 2 years, it was changed to about 10:30. So this dashed line denotes when it was reached approximately 10:30 equator crossing time. And so until in recent years, it stayed very close to 10:30. So this dashed line into early 2000, this denotes like the last orbital correction for Terra. So after this, it's a projectile. So you can see it's now quite far away from the nominal. And for Aqua, it's been actually closer to 1:35 PM for most of its life. So it's close to 1:30, but not quite. And it's been within about 5 minutes of that until early 2021. So that was the second dash line here denotes the last orbital correction maneuver for Aqua. So after that, it's been a projectile, so it's orbit decaying. So MODIS is special because it's the only wide swath, high resolution 1 kilometer native SST for the PM for 2002 to 2011 until we had VIIRS, and the AM orbit until we had Metop A, AVHRR FRAC. So the motivation was extending the L3S LEO PM record back to 2002 and the L3S daily back to 2000, which is the earliest Terra SST. So as of right now, ACSPO MODIS RAN1 data is available in L3C data format at CoastWatch. So it's documented in this journal paper here. And the archival of the L2P, L3U is also being explored elsewhere. So to at least find some place to archive the L2P, which is very high data volume. So I'll give a overview of the ACSPO SST algorithm. So ACSPO files report what is referred to as sub-skin SST. So this is sensitive to skin SST, and it's calculated using the nonlinear SST equation or NLST equation. So it's given here. So this equation is a combination of brightness temperatures and by the temperature difference multiplied by, so TS is the retrieved SST. So then the T is subscript number is the channel BTs, so 3.7, 11, and 12 is what we use. Theta is the zenith angle, solid zenith angle, and S is this geometric factor here. And T0 is the first case SST in CMC level 4 SST. So one thing we know, we do not subtract the typical 0.17 Kelvin mean cold skin effect. So our SSTs are on mean bias against in-situ SST as drifters is 0. So we use a separate set of coefficients for night, so solid zenith angle bigger than 90 and day is less than 90. In terms of evolving the 3.7 micron band are omitted during daytime because we can't use it because of solar contamination. So we also report a second SST, it's called the depth SST. So this calculated using the same equation, but using piecewise regression. So we have multiple sets of these coefficients based on atmospheric conditions. And you can obtain this depth SST from ACSPO files by subtracting SCS bias from the subskin SST, the main SST that's reported in the files. So the depth SST agrees better with in-situ SST from drifters and tropical moorings, but the cost is reduced temporal and spatial gradients. So if people are familiar with SST retrievals, that means lower retrieval sensitivity. So the second important part of the ACSPO is the ACSPO clear sky mask, so or ACSM. So the purpose is to identify clear sky pixels in which accurate SST retrievals can be made. So it's often referred to as cloud mask. So that's because the vast majority of masked pixels are due to obstruction by cloud, but it's not the only reason we mask pixels. So they can also be masked because sensor issues, aerosol contamination, or simply atmospheric conditions not represented in the SST training set. So it's more like a good retrieval mask than a cloud mask. So to apply the mask, the users only select pixels with quality level 5. So it's sort of a quality underscore level variable in our GTS2 files. So this figure shows an example Aqua MODIS SST imagery over the Chesapeake Bay in August of this year. So left is full sky. So basically it's when we attempt to retrieve SST in the full domain, full sky domain. And you can see there are clouds here and clouds here and over here. And then you on the right shows the same figure, but with the cloud mask rent and OLED. So that's a gray. So that's the ACSPO clear sky mask. So and also we can see the black curves here are the indicator for front, thermal front. So we have two layers. So it's the existence of so it's a binary mask for like is this a front or not, and then we also report the gradient in Kelvin per kilometer. So this slide is an overview of the validation of MODIS RAN1 against drifters and tropical moorings for nighttime. So this shows monthly global validation statistics against ICOM drifters. So basically every point that you see on this time series is a monthly aggregate, and our matchup criteria is 10 kilometers times 30 minutes. So you can see the top panel here is the accuracy or the mean global bias, and the lower is precision, which is the corresponding standard deviation. And the left is the subskin SST, and the right is the depth SST. So you can see that both Aqua and Terra are very consistent, so in terms of bias and also in terms of precision. So the specification for accuracy, so that's mean bias of 0.2 Kelvin, and precision, that's standard deviation of 0.6 Kelvin, are met with a large margin. So the specs are denoted here by the horizontal dashed lines. And so we can, in both cases, we see when we go from subskin to depth SST, we can see noticeable improvement. So the bias is more stable in time, and the precision is lower or improved. So this is the same thing as on the previous slide, just for the daytime SST. So you can see that the precision is degraded compared to the nighttime due to the absence of the 3.7 micron band, which is expected. So the standard deviation, the precision is higher. And also we can also see that we have about a 0.2 Kelvin oscillations or seasonal variation in the bias. So we used to think this was just diurnal variations, so the skin depth difference, but we see the same thing for Aqua and Terra and VIIRS and all these platforms in very different orbits. So we think it's more likely something to do with the retrievals. So we can see that when we go from subskin here on the left to the depth, you can see there's a big improvement. So this is more than what we saw for nighttime. And so this table summarizes the 2019 validation statistics versus drifters and tropical moving. So this is 1 year from the time series that we showed on the previous slide. So we chose 2019 because Aqua and Terra were stable back then, and both MVP and NOAA ACSPO VIIRS SST was available for comparison. And we also show in this table, this corresponding validation metrics for the NASA 2019 Aqua and Terra SST datasets. So from these, we can see that you might be familiar with the mean, standard deviation, robust standard deviation. So, and then there's the number of observations, clear sky ratio, and the raw number of pixels. So what we can see, for example, let's just take the nighttime data here. So here is VIIRS 0.33, and for MODIS it's about 0.32. So for nighttime, MODIS is very close to VIIRS, only about 0.100 of a Kelvin worse in a statistic, so very comparable. However, here if you go to the daytime, you can see about 0.42 precision for Aqua and Terra, about 0.38 for VIIRS. So for daytime, there is a bigger gap in performance. So VIIRS performs better because we have the additional 8.6 micron band, which we can't use for MODIS. It's there, but it's not usable. So also we can see the NASA, Terra, and Aqua statistics here at the bottom two for day and night, and you can see we compare favorably compared with them in terms of standard deviation and robust standard deviation. And we can also see in all cases that when we apply SST bias, we can correlation we observe in a consistently better performance metrics. And also one other thing that's mentioned, that the clear sky ratio. So that's a new specific requirement from JPSS or NOAA that it must be 18%. So we can see we are meeting that with another specs in all cases. So in addition to accuracy and precision, another important metric is the temporal stability. So this is often referred to as drift, and it's measured in Kelvin per decade. So this captures the long-term trends in SST bias to the drift in sensor calibration. So as far as I know, there's no formal NOAA requirements, but our goal is to keep this drift above about 0.05 Kelvin a decade. So this quantity, the stability is quantified using a time series of bias against tropical moorings. So that's the upper figure for nighttime SST. So we subtract the seasonal trends to just see the long-term trends. So you can see that, and the mean here of the drift is given here for both Aqua and Terra. You can see they're very low. They're below 0.01 Kelvin a decade in both cases for nighttime SST, both in a subscale and depth SST. So this is, and there's excellent agreement also between Aqua and Terra in both cases. So for daytime, we are forced to we don't just use the tropical moorings, we also use the drifters because there's very strong diurnal warming in the tropics, and the tropical moorings are measured deep, about 1 meter. So, and it's also very thick or humid atmosphere, which is difficult with the daytime retrievals to deal with. So we use the whole drifters and tropical moorings for this validation for daytime. So you can see that immediately they're not as good, like we don't expect them to. So they are like noisier, and there's some drift that you can see. But you can still see that if you look at the numbers, they're both for subscale lower than 0.03, closer to 0.02 for Aqua and Terra, and for the depth SST they are below 0.01, but they are like more variation in time though. So during RAN1, special efforts were taken to address the residual thermal emissive bands calibration anomalies. So this affected both mid-wave or mid-VIIR and long-wave infrared long-wave or LWIR bands. So in RAN1, the brightness temperatures in all SST bands have been stabilized. So we did this via analysis of observed minus modeled as OM BTs. So all the validation results that we shown on previous slides were all based on these stabilized BTs. So we observed 3 kinds of calibration anomalies. So these are all documented in our journal paper here. So we observed step changes in the early mission Terra mid-wave IR BTs. So that was due to changes in MODIS operating conditions or configuration. And we also observed in a Terra MODIS calibration anomalies due to variation in the blackbody temperature. And finally, we saw residual drift in Aqua and Terra BTs. So this is over the course of the mission, they drifted by about 0.05 Kelvin in Aqua and Terra SSTs over their 20-year missions. So I'll give a bit of a background for these, how we did these calibration mitigations. So these are the mitigations due to the Terra MODIS configuration. So since its launch, the Terra MODIS instrument has operated in different configurations. So you can see there's the AA1, there's the A-side electronics and an A-side formatter. Then it switched to BB on this date, and AA back to AA on and then finally ended up in the AP configuration for from 2002 to present. So what exactly these configurations are not important, but the important part is that when we changed configuration, we can see this. We noticed jumps in SST bias or SST. So the top figure here shows daily aggregated global mean bias of ACSPO Terra subskin SST against a CMC level 4 foundation SST. So red shows without any calibration. So basically, when we saw the first configuration change, we have about 0.1 drift and a jump and another 0.1 when the second change happens. So, and if you look at the bottom figure, this shows the corresponding observed minus model BT for the 3.7 micron channel. So we saw the same effect. So there, it's less pronounced because it's amplified, but the jumps are amplified by the SST algorithm. So what we did was just basically read off the jump from the observed minus model BT's time series and just plugged back and corrected the L1B. And so the blue SST time series is what we observed after the calibration mitigation of fixing the BT jumps. So we also performed some mitigation due to variations in the MODIS blackbody temperatures. So it's mainly during warm-up cooldown or WUCD events. So during this event, the MODIS blackbody temperatures vary between ambient instrument temperature. So it's about 270 Kelvin, and the top is about 3.15 Kelvin. So the purpose of this is to characterize the thermal emissive band's response to noise. And these events last about 2 to 3 days and are typically performed quarterly. So example of one of these warm-up cooldown events is shown in the upper figure. So it's about 2 to 3 days. So initially it's cool down, warmed up, cool down, and back to nominal. So this shows the anomaly. So the nominal, so the blackbody temperature minus the nominal. So 0 is the nominal value. So this is during a specific warm-up cooldown exercise in 2009. So this mainly affects the mid-VIIRS channel, so it results in about 0.05 to 0.15 Kelvin one bias in Terra nighttime SST. So this bottom figure shows like a time series of daily aggregated global mean bias for ACSPO Terra SST against CMC level foundation, CMC level 4 foundation SST. So blue is without any mitigation, so you can see every time there's a warm-up cooldown event, you can see this spike. And the red is without with the calibration and with the mitigation. So when you see that the spikes are gone after we performed this mitigation. And also for comparison, we also shown the NASA ARC 2019 results, which has the same anomalies as our uncorrected BTs. And I note that only Terra is affected. We didn't see anything like this for Aqua. So these are corrected for using an empirical model. So it's based on dependency of observed minus model BT bias, dependency on blackbody temperature anomaly. So basically, we just show an example here for Terra MODIS mid-VIIRS channels 20. So we can see here the blackbody anomaly. So at 0, we obviously have no bias, but when the blackbody is cold, we have positive bias, and then again when the blackbody is warm, we have warm bias. So black is the results, experimental results, and then red is our piecewise linear model. So we use this piecewise linear model to correct the BTs in the L1B. So these model parameters are trained using all warm-up cooldown cycles prior to 2020, April 2020. So something special happened then. So on April 2020, the Terra MODIS nominal BPT was changed from 290 to 285. So this changed how the warm-up cooldown biases materialized, and so we had to retrain these model parameters on the data after this date. So that's not the only thing that happened when the blackbody temperature changed. So the nominal blackbody temperature switch also caused about 0.04 to 0.07 Kelvin discontinuity in the mid-VIIRS BTs. So this is also addressed in RAN1. So if you don't account for this jump, we see about 0.05 Kelvin jump in SST. So this lower figure shows the daily mean bias against CMC level 4 and SST around this date here. So like the second dashed line here is when the blackbody temperature was changed. You can see like without any mitigation, which is the red, you can see a jump about 0.05, and with mitigation in the blue, that is gone. So this time series is a bit complicated because there was a warm-up cooldown event, and then after that event, it was the nominal blackbody temperature was changed. So it looks a bit more complicated. So finally, we performed mitigation of the MODIS calibration drift. So residual drift in MODIS brightness temperature was discovered early during RAN1 production. So in RAN1, the BTs are detrended prior to doing SST retrieval. So we use analysis of the observed minus model Aqua and Terra MODIS BTs. So the upper figure shows global mean bias of MODIS nighttime subskin SST minus in situ from drifters and tropical moorings without, so that's the upper figure, and with the trending of BTs. And we can also in lower show the corresponding NASA R 2019 results. So you can see in the upper figure without any mitigation of this drift, you can see early the first half of the Aqua mission was drifting downwards, then remained stable, and Terra was stable early on, and later in the mission it started drifting upwards. And on the lower one, we can see what happens when we fix address the drift. So like now the agreement is excellent. And so as for the NASA R 2019 SST, so the Aqua is very stable. So by the way, they use different channel than we do channels, but the Terra SST is drifting quite upwards quite a lot. So as I mentioned before, the primary motivation for this MODIS RAN was inclusion or extending L3S LEO. So this slide kind of covers the inclusion of MODIS RAN1 in L3S LEO version 2.81. So there's the PM orbit, L3S LEO PM from afternoon PM orbit satellites. And so these products are reported twice per 24 hours, like I mentioned earlier. So before in 280, it only includes NPP and NOAA 20 VIIRS. But now in version 2.80, we are including NOAA 20 VIIRS, and also we are including Aqua MODIS RAN1 SST. So this is included until the March or end of 2022 when the Aqua drift, orbit drift became significant. So the most important part is this extends the record from 2012 to 2002 of L3S LEO PM. And similar for the daily, so this includes as mentioned before, all high-res ACSPO SST from LEO sensors. Those both in day and night data, one file per 24 hours. So version 2.80, the previous version included Metop-FG and MPP and NOAA 20 VIIRS, but in NOAA 21 and the newer 2.81, we included NOAA 21, Aqua, and Terra. So the most important part here is by including Terra, we extended the record from 2006, which was the earliest Metop-SST, back to 2000, so was the earliest Terra SST. So these figures here show the time series of the clear sky ratio of L3S LEO daily before, and the previous version was 2.80 and the new version was 2.81. So you can see, most importantly, the PM is now extended back to 2002 when we launched Aqua, and Terra and the daily is now extended back to when we launched when the Terra SST is available. And we note that after about 2018, when we have 2 VIIRS sensors, like the typical clear sky ratio is about 65%, which is quite impressive. So as for summary and future work, so the first NOAA MODIS Reanalysis MODIS RAN1 was produced, so using ACSPO version 2.80. So that includes both Terra and Aqua. And MODIS calibration aspects are mitigated, so step changes in long-term drift, and performance metrics, accuracy, precision, and stability compare favorably to existing datasets. So the dataset is currently available at NOAA CoastWatch, so this is in a 0.02 degree L3C format, and MODIS ST is included in ACSPO L3S LEO version 2.81. And archive of L2P and L3 data is being exported. So as for the future of MODIS RAN, so we plan to reprocess MODIS SST. We can record using ACSPO 3.0, which is planned for release in late 2024. So the updates in 3.0 will be mostly aimed at the clear sky mask and aimed at reducing the overscreening of dynamic regions. And we also might need to do some additional mitigations for Aqua and Terra orbit degradation. So as of this writing, the effect on ST by the orbit degradation is small, so we don't really see it in in-situ SST when we compare to in-situ SST. But as the satellites drift further, we might need to perform additional mitigation procedures when the orbits drift further.